Alright guys, today we're going to talk about how to transform the graphs of any function. So the problem you're facing is relatively simple. Let f(x) be the original function or the parent function, and we usually pick a basic function such as x squared, the basic quadratic function, or 3 to the power of x, the basic exponential function. And we're going to transform the shape of f(x), right? Let gx be a transformed graph or function of f(x), and gx is represented by a times f of k times x minus d, then finally plus c, right? You're going to do something to f such that becomes g. And the question you're facing is, how do you graph g given that you understand the behaviors of f? Now, this is usually covered in grade 11, and they go a lot more in depth in grade 12. So today we're going to look at how do you transform any graph, right? It's not particular to, say, polynomials or exponential, but rather what's the general approach and guideline to transform any point of any curve. Okay, so in order to understand transformations, we need to understand there are 4 kinds of major transformations represented by 4 parameters: the a value, the k value, the d value, and the c values, right? So we're going to explore how these 4 parameters at their respective locations change the shape of the transformed graph. So let's start our discussion with the a parameter, which represents the vertical stretch, and we're going to use sine x as our parent function fx. So we have the original curve sine of x as the red curve, and let's see what happens when we replace a with different values. So I'm going to start off with a value greater than 1, such as 2, right? What about 2 times sine x? So you see that for sine x, I achieve my maximum when x is equal to pi over 2, and the maximum y value will be 1, right? So in 2 sine x, the blue curve, I still achieve my maximum value when x is equal to pi over 2. That doesn't change. But my maximum y value now gets multiplied by 2 and becomes 2. And what if I multiply this sine x original vanilla by a 1/2, right? So now your maximum y value will be cut by half, or it will become half of what it was before. So it will go from 1 to 0.5 as represented by the green curve. What if you change your a to be a negative value, such as negative sine x? Well, you will flip the function, right? This is known as a vertical flip. So you will no longer have a maximum value, you have a minimum value, and the y value goes from 1 to negative 1. So it goes from maximum to minimum and has a value of negative of what it was before. Now the next parameter we're going to talk about is the k value, also known as the horizontal stretch. Now it's very important to not confuse the horizontal stretch and the vertical stretch. Don't confuse where they happen. Remember, the a stretch, or the vertical stretch, happens outside the original parent function f, right? And the horizontal stretch happens inside the original fx. So for example, sine of 2x, this is a horizontal stretch, right? Or horizontal transformation, whereas 2 times sine of x, that's a vertical stretch. So don't confuse the positions of the 2 parameters. Now let's talk about horizontal stretch in detail. We know that for the original sine x curve, right, the red curve, the maximum happens when x is equal to pi over 2 and the y value is equal to 1, right? So if I do horizontal stretch, remember, this has nothing to do with the vertical, right? So my y maximum value will forever be 1, unlike in the previous kind of transformation, right? So 1/2, for example, sine of 2x, remember, my maximum y value is still going to be 1. But I will achieve that maximum a lot quicker, 2 times quicker. Instead of achieving the maximum when x is equal to pi over 2, now it becomes pi over 4. How did I get pi over 4? Well, you take the original x value, you divide it by 2. I know this is very confusing and counterintuitive because sine of 2x, you're probably expecting to multiply every x value by 2, but you do the opposite. This is the counterintuitive part. So when you multiply the inside of fx by a value greater than 1, it's actually a horizontal compression, right? And of course, the opposite is true. Let's suppose I multiply the inside of the fx, or the inside of sine x, by a value less than 1, but greater than 0, right? Such as a fraction of 1 over 2, then that's a horizontal stretch, right? So I achieve my maximum a lot later, right? Not at pi over 2. This time, as indicated by the green curve, you achieve it at pi, right? You basically multiply your period, extend your period by 2. Now, what happens when you multiply the inside, right? You replace k with a negative value. Well, that's known as a horizontal flip about the y-axis. And that's all for the stretches and compressions. Now we move on to the shifts. So the next parameter is the horizontal shift, the d value. So, of course, we use sine x, the original red curve, as our reference. What if, right, you replace d value with a positive value? So that means you take x, subtract a positive value. This is actually also very counterintuitive. It's actually a shift to the right. Remember, x minus 1 is the blue curve. It's a shift to the right. We know that the sine x originally starts at 0, 0. Now you shift to the right by 1 unit. You start at 1, 0. And of course, the opposite is true if you do sine of x plus 1, right? So anything you add to the x, then that's a shift to the left. So originally, a sine x starts at 0, 0, but in the green curve, it starts at negative 1, 0. So all the horizontal transformations are kind of like counterintuitive. It goes opposite, right? If you multiply, it's a compression. If you add, it's to the left. So now we move on to the final transformation, which is the vertical shift, the c value. Of course, our original sine x, right? Its maximum happens at when x equal to pi over 2, and the maximum y value is 1. So if you add 1 to the end, remember, not inside the function, right? Not like the d where it happens inside the bracket, but if you add the 1 to the end, then you lift your entire function up. Every point on the function gets moved up by 1, right? So your maximum as well, right? Originally happens at pi over 2, 1. Now it happens at pi over 2, 2. Now, what if you subtract 1? Well, the opposite true. You move it down. Every point on this curve gets moved down. So your maximum happens at pi over 2, 0. And that's all the basic transformations. We're going to go through this, or review this through an example. Right? In example 1, we suppose that we have a function fx, we just don't know what it is, and we're given one point a on fx, right? We want to know, if I apply a bunch of transformations to fx, where will the new coordinates of a be, right? Or what will be the new coordinates of point a? So my transformation is negative 2 times, f of 4 times x minus 3, then in the end I add 1, right? So of course, I don't know what exactly f is. I just know I'm just given 1 point on f. So this is a pretty general case. So let's start with the origin. Let's go through all the transformations. First, I'm gonna deal with the vertical stretch, right? So the negative 2. Original point is 1, 2, right? If I deal with a vertical stretch, that means I multiply my y value, which is 2, by negative 2. So that means the point after the vertical stretch, it becomes 1, negative 4. Right? Now I'm going to deal with my horizontal stretch, or in this case, it's actually compression, because remember, right? If it's multiplied by 4 inside f, that means every x value gets divided by 4. So that means my 1, negative 4, if I divide the x value by 4, it becomes 0.25, negative 4. So that's where the point will be after experiencing both vertical and horizontal stretch. Then third, I'm going to consider my horizontal shift. I'm going to move everything to the right by 3 because it's x minus 3, right? So remember, its minus is to the right. So 0.25 becomes 3.25. So my new point after vertical stretch, horizontal stretch, and a horizontal shift becomes 3.25, negative 4. And finally, I'm going to do my vertical stretch. It's the simplest, right? You do it in the end, so that you move everything up by 1. So all the y values are affected. They go up by 1. So it goes from negative 4 to negative 3, so that my final coordinates of the point A is 3.25, negative 3. This is the general approach of changing or transforming any function fx, even though you may not know the equation of the function itself.